Okay. Next lecture of the day. Okay. Now, at the end, in the end of previous lecture, we talk about the solution of these differential equations with these given initial values. And we know that the total response consists of two parts. This part, which will decay to zeros when time goes to infinity, represents the transient response of the system. And the remaining part, which will always be there no matter how time progresses, is the steady state response of the system. Now, in this figure, distance represents this curve of transient response. And this curve, solid red line, represents the sum of these two terms, which together is the steady state response of the system. By acting these curves together, that is, by combining transient and steady state response together, this is what the overall total response look like. Okay, so let me make some remarks about the properties of transient response. Transient response represents the short-term behavior of a system. It captures the system response as it transitions from its initial state to its final stable state. Okay, it represents a process of changing, of going from starting from the initial conditions to all the way up or all the way down to the final target, which is the steady state of the system. Decays over time. In a stable system, note that the system has to be stable. If the system is stable, the transient response decreases and eventually dies out as the system approaches steady states. Okay, so the transient response, since it is transient, it means it will not always be there. It means it will eventually go away, disappear as time goes to infinity. And the next remark is also very important. What is the shape of the transient response? What is the basic pattern of the transient response? The transient response is influenced by the location of poles and zeros. Okay, so transient response is actually determined by the transfer function, or more specifically, determined by the locations of the poles and zeros. That is a reason why the locations of poles and zeros matters. Okay. Now, in essence, Paul defined the what of the transient response, which means the form of the transient response. For example, the form of the transient response can be decaying, can be oscillatory, or can be unstable. When we say unstable, I mean it will diverge as time goes to infinity. Okay, it will blow up. Okay, it will go without any bound. While zeros shape the how, that is the magnitude, as well as the fine details of the response. Okay, so the patterns of transient response, as I said, is really determined by the location and poles and zeros. And Paul basically determined the basic response pattern of the transient response. And zeros, the location of zeros, determine the size as well as the remaining fine details of the transient response pattern. Okay, so that is, as I said, why the locations of poles and zeros are important. Okay, now let's switch gear. Now I want to make some remarks about steady state response. If transient response is correlated with short-term behavior, then by contrast, steady state response is related to long-term behavior. The steady state response is the part of the system output that remains after the transient effect has settled down. It reflects how the system behaves after it has time to fully respond to the input. Okay, this statement is really a very important, really carry a very important message. Steady state response represents the response of the system when the input to the system has been fully appreciated or fully take effect. Okay, so that means when you apply an input to the system, you do not get what you want immediately because it will take time for the input to take full effect. That is the nature of dynamic systems. Okay, so steady state response is the result, the overall result of the input, okay, because the system needs amount of time to fully respond to the impacts of the input. Now, stable output, the second remark is related to stable output. In a well-designed system, the steady state response should match a desired output. Okay, or reference our signal, or let's say target output. Okay, closely, meaning that any errors or deviations should be minimized. Okay, so if steady state response is the so-called desired output or target output, so the steady state value of the output should be as close as possible as the designated value that we want a system to reach. Now, so of course, okay, there is always an error in the real world. So this is the reason why we need to know how large our steady state error is. Now, here, the steady state error is defined as the difference between the desired output. Sometimes we call this desired output, as I just said, target output, and the actual steady state output is called the steady state error. So the error is the desired output minus the actual output. E is why this is ideal output minus what is real actual output. All right, ACTUL. Okay. Now, from a mathematical point of view, the steady state response is typically related to the long-term behavior of the zero state response due to the external input. Where does steady state response come from? Transient response come from poles and zeros. Steady state response come from external input. Okay, not an entire external, not the entire zero state response, but the long-term behavior of the zero state response. And zero state response is, of course, the result of input. Okay, so the steady state error is really determined by the system as well as the input. All right. Now remember that total response actually consists of these two parts. Let's assume the system is asymptotically stable. We will talk about asymptotic stability in a few minutes. Okay, but let's just assume you know that the system is asymptotically stable. That their input response is a component of the transient response. Okay, their input response for asymptotically stable system is always a part of the transient response. In general, we want this component to disappear as rapidly as possible. Okay, why is that the case? Okay, this is the total response. This is the zero input response. This is the zero state response. In control, we can manipulate F to achieve desired zero state response. But F, which is the input, has no impact on the zero input components, on the zero input response, because it comes from initial conditions. there is nothing we can do about it. If we cannot do anything about it, what do we want it? What do we want it to happen? We want it to die out naturally, not by us, but by the nature of it is, but by its own nature. All right, by its own nature. If this die out naturally as time progresses, then it won't stand in our way. We can manipulate it to achieve the output we want, because this term, although we cannot do anything about it, it will go away by itself. It will die eventually. Okay, well, that would be one of the bad things happen in life. If you have an enemy and you cannot do anything about it, the bad thing probably I can hope for is the enemy will die from a disease or from an accident, whatever it is. Okay, I'm just joking. I don't want anybody to die because of me. All right, but again, that tells us what the solution is. Okay, there is something I can do. I cannot lay my hand on. There is something that is untouchable, but it is part of the solution. What can I do about it? It's untouchable. Fortunately, it will die out by itself. So even if it is untouchable, it will go away. It will not become a factor of the equation. Okay, but there is a condition. This system has to be stable. Okay, and since I wanted it to disappear, therefore I want it to go away as soon as possible, or as rapidly as possible. All right. So now finally come to the definition of stability. Now the first thing you do. No, I'm sorry. One of the first. This is embarrassing. Okay. Now, one of the first things we need to know about the definition of stability is that there is no stability when it comes to the definition of stability, which means stability being a very understood concept, it is actually not very well defined. All right, there are many different types of definitions for stability. Okay, and we are only talk about the two of the most popular definition for stability. The first stability is what we call asymptotic stability, and it's a stability of narrow sense. Okay, if an LTIC system, again, LTIC stands for what? Linear time invariant continuous system, has n distinct characteristic groups. Okay, let's just, for the benefit, okay, for simplicity, for the sake of simplicity, let's just assume all the poles are real, and they are all distinct, non-repeated real numbers. Okay, now the zero input result is given by this. Okay, now it can be shown that. I'm sorry. Let me I made a mistake. So let me rephrase the statement again. Here we have an LTIC system, and it has n distinct characteristic groups. And these n distinct characteristic groups can be real numbers, and it can also be complex conjugate numbers. All right? Okay. So we all know that the zero input response, these are the modes, and the zero input response are the linear combination of all the modes. Okay, what is a mode? Mode is a base response pattern of the system. Okay, we have shown. Okay, now if the system is asymptotically stable, then it means that these modes, when time goes to infinity, it has to become zero. Okay, now for this to happen, it can be mathematically shown that the real part of lambda, that is the real part of the the poles has to be smaller than there. Okay, so the final conclusion is that an LTIC system is asymptotically stable if and only if all the characteristic roots are in the left half plane. Left half plane. LH means denotes left half plane. Okay, their roots has to be located on the left half plane of the X plane. Okay, now what does it mean? It means that, let me put it this way. In the X domain, the independent variable is S, right? In the X domain. After taking the Laplace transform of the differential equations, and we transform everything into the X domain, and X domain therefore become the independent variable. Okay, in the time domain, the independent variable is of course T, which stands for time. In the X domain, X is a complex number. Okay, this is the reason why we call X complex frequency. All right, now, so with that in mind, I can set out an X I'm sorry for my poor writing. X complex plane. Okay, a plane, of course, is a 2D representation. Now, for the horizontal axis, we have the real part. Okay, so this is real. Okay, for the vertical axis, we have omega, or simply j omega. All right. Now, this is, of course, the imaginary part of the system. So, what do I mean? For example, if X, let's say, is just 4 plus 3j, okay? J is, of course, the imaginary number. Then the location of X is here. This is 4, since this is 4. Now, since this is 3, all I need to do is identify the point of 3 at the imaginary axis. And then here, this is S. Okay, so X can be represented in the complex plane. Okay, and this is what a complex planes of X look like. All right, now here lambda corresponds, of course, to S. Okay, now to a system to be asymptotically stable, it means that this real part of X has to be negative. So that means the location of X has to be on the left half plane of the left half plane of the X complex plane. All right. Now, before we go forward, I want to make some remarks about why stability is important and even how important it is. The first reason is stability has everything to do with safety. Stability is essential for safe operation. An unstable system is dangerous and can lead to catastrophic failures. Okay, for example, a boat can sink, an airplane can crash. Okay, and you don't want that to happen. And the second thing is it has also everything to do with functionality. A system must be stable to be predictable and perform its intended tasks, which means an unstable system is by definition out of control and non-functional. Okay, so when it comes to control, of course, we need system to be controllable, to be function, but unstable, if we encounter instability, that destroys everything, okay? And the third reason for stability is equipment protection. It prevents a system response from growing without bound, which would drive physical components to their limits, okay? If you have infinite large force, if you have infinite large current or voltage, no physical hardware could sustain that, can survive from those infinitely large physical quantities, all right? Okay, so, and would drive physical components to the limits and cause them to break or burn out. And we don't want that to happen. So, so stability, therefore, is a non-negotiable first step in design, which means in designing a system, the first thing we need to make sure is that the system, the system to be controlled in its open loop configuration, is it stable? Okay, if it is stable, is it stable enough? That is, after absolute stability criterion has been satisfied, I also need to look into relative stability. Okay, but if the stable open system is unstable, the first thing come into mind as a control engineers is that how do I fix that problem? How do I solve the instability problem? How do I make sure that the open loop after feedback, the closed loop system can be a stable system? That is, after using feedback, all the poles of the closed loop system has to be on the left-hand side of the X complex plane. Okay, so what can asymptotic stability give us? A system is asymptotically stable if the zero input response approaches zero as time approaches infinity. Okay, because that's exactly what we want. Okay, what we don't want is a system that is asymptotically unstable because its zero input response will approach infinity as time approaches infinity, and everything will crash or break down. Now, there is a boundary between these two conditions. That is, a system is marginally stable if the zero input response neither decays or grows, but remain constant or oscillates. Okay, if in steady state, that is when time goes to infinity, for marginally stable system, the output will either always be a constant value or it will always oscillate up and down without an end. Okay, now let me emphasize again, asymptotically stable system has closed loop transfer functions which pose only in the left half plane. When we say left half plane, we mean left half X complex plane. All right. Now let me emphasize again: if a system is asymptotically stable, their input response will always vanish as t goes to infinity. Now this is a picture of the X plane. Okay, the horizontal axis corresponds to the real power, and the vertical axis represents the imaginary number. And this is lambda, okay, lambda, right? Okay, just think of it as S, all right? Okay, we use lambda when we was in the time domain. Okay, we use S when we were in the Laplace domain. All right. Now, so for this part, when all the poles are located in this part of the S plane, the system is asymptotically stable. If it's in the right half side of the plane, the system is asymptotically unstable. And if the poles are located on the real imaginary axis, that is the vertical axis, then the system is what we call marginally stable. All right. Now, what is the relationship between the location of the pulse and the response pattern of the system? Okay. Now, let's say here I have a simple pulse, which is a real number. Then its zero input response will look something like this. Okay, where A is this distance, the distance between this pole to the imaginary axis. So it will grow without it will decay monotonically to zero without any oscillation. Okay. Now, if by contrast the pole is located here, which apparently is on the right half side of the plane, then zero input response will grow monotonically and exponentially to infinitely large, to infinity, without any bound. Okay. Now, if the pole is located at here, origin, then this is what will happen. It will always be a constant. All right. If I have double poles at origin, then the output will also be unstable. Okay. Now, let's say here I have a pairs of complex conjugate poles. All right. And what the response will look like is this. Why is this the case? Remember that when dealing with, we talked about this before. If when dealing with E to ST and X is a complex number, then it can be shown that EST plus E S star T divided by 2, where X star represent the complex conjugate of X. This will give us E to sigma T cosine omega T. Ring a bell? Okay, we saw this before, right? When last time we saw this result, I told you that the real part of X determines the overall shape of the response because it determines the envelope of the response, right? And then the imaginary part of X determines the speed of the oscillation pattern. So in the X plane, this, I'm sorry, let me switch to this. The distance between the pole to the real part, to the real part of the plane is sigma, right? Similarly, the distance between the imaginary axis to the location of the pole is, I'm sorry, this is sigma. What am I doing? Okay. This is omega, all right? And this S is, of course, sigma plus j omega, all right? So this part, which is the distance between the location of pole to the real axis, to the imaginary axis, to the vertical axis, actually determine the envelope of the response pattern of the system, okay? Now, so if you want a system, want this response to die out faster, what you need to do is more sigma, more negative, right? So what you need to do is to move the location of this pole further away from the imaginary axis. All right? Okay, this is first time we talk about the impact of the location of the pole on the response of the system. This is first time we talk about it. We will talk about this particular property again and again in the future. All right? But why do I want to do that? Because the location of the pole matters. Okay? And what will happen if you move the pole further up and down at the same time? It will increase omega. As a result, it will increase the acceleration frequency of the response. Okay? So this is a system with a stable system with a pair of complex conjugate poles whose are located on the left-hand part of the left half plane of the x-plane. Now, if the poles, this pair of complex conjugate poles are located on the other side of the plane, and this is what will happen. It will go increase without bound, okay? And if this pair of poles are located on the imaginary axis, which means this system is what? It's a marginally stable system, and that's its response pattern. All right? Okay? So that defines so the location of the poles defines a system is asymptotically stable or not. So asymptotic stability has everything to do with the location of the poles. Okay? And as long as all the poles are on the left half plane of left half side of the complex plane, then everything's okay because the system is therefore asymptotically stable. Now, as I said in the beginning of this part of the course, which discuss stability, the definition of stability has no stability. Okay. As a matter of fact, there are many different definitions. Another popular definition of stability is what we call bounded input, bounded output stability, or just simply BIBO stability. It provides an external and practical definition of stability. A system is considered to be BIBO stable if for every bounded input signal you apply, the resulting output signal is also bounded. Okay, you apply a signal, doesn't matter what it is, doesn't matter what waveform is. It really doesn't make any difference when it comes to the definition BIBO stability. The only requirement is that the signal you apply, that is the input, its magnitude is bounded. If you apply such a bounded magnitude signal to the system, and you can guarantee that the output will, no matter what kind of output it will get, it will not go without, it will not increase without any bound. If that condition can be satisfied, then we say the system is BIBO stable. Okay? All right. For example, a sine wave is bounded because its value always between -1 and +1. Okay. A constant DC voltage is also bounded. All right. Now, why? Now, the next thing I want to talk about is the limitation of asymptotic stabilities. Okay. Now, when it comes to asymptotic stabilities, what we really care about, what we have to pay attention to, is the zero input response of the system. All right. Asymptotic stability describes the inherent nature of the system. It answers the question if left alone after a disturbance, will the system return to equilibrium? Okay. What do we mean by that? Okay. Let's imagine a situation. Okay. Now, here is our surface. Here is a ball. If you move the ball around, okay, let's say you disturb it by a very small force, and let's say it will go to here, and then you don't do anything about it, then ball will oscillate up and down, left and right for a while, and eventually it will come back to its so-called equilibrium position. And this is what we call a stable condition. Okay, the system here is asymptotically stable. By contrast, if the surface look like this, and the ball is located at the top of this surface, like located on the top, very top of the a hill, okay? If nothing happened, okay, if this ball has not been excited by any input, then it will stay in that equilibrium position forever and ever. But once you excite it, even with a very small force, then it will go down and eventually go all the way down without any limit until eventually it hits something, okay? So this represents a stable system. This represents a scenario of instability. Asymptotic stability answers the question, if left alone after a disturbance, will the system return to equilibrium, all right? Will it come back to this equilibrium position? This, it will, yes, it will. But in this scenario, no, it will not go back to its original equilibrium position. Therefore, such a system is considered to be asymptotically unstable. A controller's job is to generate the right input to force the system to behave as desires. Okay, so a controller job is we do something about the zero-state response. However, asymptotical stability only care about this part. It only care about the zero input response. Okay, so a goal of control engineering is to design controllers that stabilize and regulate systems, ensuring desired performance even when the operating system is inherently unstable. Because asymptotic stability only takes this into account. It does not mention anything about FFT, the input. So if you don't apply any input, of course, for unstable system, this will go to infinity, okay? And that will create an instability problem, and the system will definitely crash. But remember that the total response is not just about the input response. As a matter of fact, the goal of control is to generate, to come out with a good FFT, a good input, so that the total response can conform to my need. Okay, it can match my requirement. So one of the limitations is asymptotic stability is that it has not taken zero-state response into consideration. All right. Okay, the final part of this PowerPoint slide and the final part of today's lecture is we want to talk about final value theorems, which is a very important mathematical results in Laplace transforms. Now, final value theorems tell us that if you want to find a steady state value of y of t typically is the output of the system, okay? We want to know the value of the output when time goes to infinity. That is, we want to know the steady state value of y of t. How do we do that? We can do it in time domain, but we prefer to do everything in S domain because in S domain, the the entire mathematical derivation process is much more simpler. It's easier to manage those mathematical samples since we don't have to deal with differential equations. We deal with algebraic equations. Now, to determine a steady state value, what you need to do in the X domain is first determine the Laplace transform of Y and then times it by S. And finally, assume X approach 0 and see what happens. Okay? Now, let me make some remarks about final value theorems. What is its purpose? It helps us quickly to predict the steady state values or the final values of the system output. That's why it is called the final value theorems. Answering the following question, where will the system settle after all transient behavior has died down? Okay. Now, primary application is calculating steady state error. You know the steady state output, and the next thing you want to know is the steady state error. To check if the steady state error, if not 0, if it is in the acceptable range, is such a steady state error tolerable? Okay, can I tolerate such a steady state error without compromising my control mission? Crucial condition for use, okay, it's not always completable. There are some preconditions that need to be satisfied before we can use final value theorems to predict the steady state output. The FFT only works for stable system. So the system first has to be asymptotically stable, where the final value is a constant, and the final value has to be a constant. It fails if the system is unstable. Why it fails? Because when the system is unstable, there is no steady state value, because by definition, the system output will become infinitely large. How you determine the value of an infinitely large number? You can't. Or it also will fail if the output is oscillates, because here it will give you a number, because you are making sure that X equal to 0. And therefore here, what you will get won't be a variable of S, but a real number. Okay? But if the function that sets the output is not a constant, is, for example, a sinusoidal signal, then it cannot be characterized or represented as a real number. And in that situation, FFT fails, or FFT cannot be applied. Okay? All right. We should still have 7 minutes. Okay, very good. Okay. After introducing FFT, let's introducing another theorems which was mentioned in the course of engineering mathematics regarding to, again, Laplace transform. Okay. Here I assume I have a signal FT. If I take Laplace transform of such a signal, I have capital F of X. So capital Fx is of course the Laplace transform of f of t. Now, next thing I want to do is to this. I delay the signal by a time units, let's say 8 seconds, and multiply it by such a unit step function. Note that based on the definition of unit step function, it means that this function will have values only after t equal to a, right? Because when t is equal less than a, the definition of unit step function tells us that the value of this unit step function has to be 0. Okay? So if I take the Laplace transform, this is actually a time delay version of f. Okay? Time delay version of f. If I take a time delay f, take the Laplace transform of a time delayed version of f. This is what I will get. What you will get is fx times e to minus as. X, no problem, is the complex conjugate frequency. What is A? A, by definition, is the amount of time delay. Now, this series is called the second translation series, and this equality can be mathematically proved. And the procedure for proving this equality is given here. Okay, it's not difficult. Okay, how do you prove this equality? Very straightforward, simply based on the definition of Laplace transform. Okay, this is what I want to Laplace transform, and this is the definition of Laplace transform, and then some simple straightforward mathematical manipulation, and you come up with this. Now, why is this important? In the course of engineering mathematics, this, again, is a mathematical property that we need to know. But why is it important? Okay, as engineers, I will not be satisfied with simple mathematical property. Okay, I care about math because only when math matters to us as engineers. Now, the second translation series provides the term e to minus as to model real-world time delays, also called date time. So typically in an X domain, what you will see is polynomials of S. Okay. It can be P of X over Q of X, right? That means you can encounter a transfer function which is made of Q of X to P of X to Q of X, where P and Q are both polynomials. Okay, so in X domain, typically what you will encounter is polynomials of X. However, whenever you see exponential function in the X domain, it only has one possibility. That is, this exponential function in the X domains correspond to time delay in the time domain. All right? Okay, so e to the minus ax in the X domain is to model real-world time delays. These delays are highly undesirable. We don't want time delays, okay, because they introduce phase lag. We will tell you why in the later part of this course when we talk about frequency domain methods, which reduce stability margins and easily make a stable system unstable. Okay, so time delay can deteriorate stability. A originally stable system can become unstable due to time delay. Why? Of course, there are some mathematical proofs to demonstrate that this is the case. But think of it physically. Time delay makes a system much harder to control effectively. They cause the system to react to the old information. To control something, you have to do it in real time. You have to perform your control operation. You have to perform your control operation based on the newest, most recent information about the system. Okay, but if there are time delays, then the control command you produce and the real situation of the system, there will be a gap between them because of the time delay. Okay, so whatever you do as a controller could be too late to manage the system to the way we want it to be because of the time delay. It's not that your control commands is not good enough. It's because your control command cannot be put in place in time. Okay, and that creates instability. All right, 12 o'clock. Okay, thank you for your participation. I really appreciate that. 谢谢，后面就交给你了。嗯，没有你。